Hello and welcome to this video for CE108 Mechanics of Deformable Solids. So this week we are still in chapter 7, we are still talking about bending. In the previous week what we saw is how to calculate the internal shear and the internal moment acting within a beam as a function of the external forces and the external moment that are applied to this beam. So for this we said that to define the internal loads that are acting within a beam, you need to use the method of section. So you need to cut the beam into two parts, and then by sign convention we define the internal shear as going down if it's applied on a right surface, or going up if it's applied on a left surface. So this is the positive sign convention for the internal shear. And then we defined the sign convention for the internal moment, which described the moment applied by the left, or the moment applied by the right to the left, or the left to the right. And so we said that this moment is anti-clockwise if it's applied on the right surface, or clockwise if it's applied on the left surface. So, and then we saw different methods. We saw that we can calculate those internal shear and internal moment by using the method of sections. We saw that a more convenient method is usually the integration method. And we also saw the graphical method that allows us to not analytically calculate the internal shear and the internal moment, but to get the trend of where how the internal shear and internal moment depends on x along a given beam, and where is the moment maximum. So the reason that in many cases the graphical method is enough is that we don't necessarily care about the absolute value of the internal shear and internal moment, but we want to see at which point of the beam the internal shear and the internal moment will be maximum, because those are the points where the stress is also going to be maximum. So those are the points where the beam is the most likely to break. So what we are going to see now this week is how to calculate the stress that is acting within a beam that is subjected to bending. So for this, there is two things that matter. So when you want to calculate the stress within a beam that is subjected to bending, so two things are going to be important. So the first thing that is going to be important are, so what is the internal shear and the internal moment. So the internal loads that are acting within the beam will be important in determining the value of the stress. But there is another thing that is going to be also important, which is the geometry of the beam. So just like what we saw in the axial load chapter and in the torsion chapter, those two things, the geometry of the beam and the internal loads, are both important to determine the stress that is acting within a beam. So for example, in the case of the axial load, the formula that gives you the normal stress within a beam that is subjected to an axial load is given by the internal load at a given position x divided by the area of the cross section. So in those cases, those two things are equally important. You have the internal load, because if you have no load, you have no stress, but also the area of the cross section is also an important property, because depending on whether this area is large or small, then the internal load is going to be distributed over a small or a large area. So this is going to affect the stress, and if it's affecting the stress, then it's affect the propensity for the beam to break. So in those cases, those two things are important. Same thing for the case of torsion. If you remind yourself about the torsion formula. So the shear stress at the maximum shear stress that you can find at the surface of a shaft that is subjected to torsion is equal to minus times the internal torque times the radius of the shaft divided by the polar moment of inertia. So here in this case, this is the same thing. You have two quantities that matters to define the shear stress that you will find on the surface of a beam subjected to torsion. The first thing is the internal torque. So the internal torque only depends on the value of the external torque that are applied to this beam. So it's something that doesn't depend on the type of material or doesn't depend on the geometry of the beam. But then you have a second quantity, which is the polar moment of inertia, which in the case of torsion is the geometrical property that governs how resistant a beam is going to be to torsion. So if you have a high polar moment of inertia, then the shear stress will tend to be low. So now if we come back to the case of bending, this is going to be the same thing. In the case of bending, what will dictate the value of the stress in a beam subjected to bending will be both the internal load that are applied, that the beam is subjected to, but also the geometry of the beam. The geometry of the beam is also going to be important in determining the value of the stress. And in the case of bending, the geometrical quantity that matters is not the area of the cross-section or the polar moment of inertia. In this case, it is the moment of inertia. The moment of inertia, which is what we are going to talk about in this first video, is going to be, in the case of bending, the key geometrical property that controls the propensity of a beam to develop some stress when subjected to bending. And in this case, what will matter more specifically is the moment of inertia of the cross-section of the beam. So if you have a given beam like this that is subjected, for example, to some moments like this, what will matter, the geometrical quantity that matters will be for the cross-section, which is this section here. For the cross-section, what is the moment of inertia I of this cross-section? So the first thing that we are going to do is to try to understand what the moment of inertia is and to provide its definition and to get some feeling about what the moment of inertia is actually capturing. So for this, what matters is what is the shape of the cross-section of the beam. So let's consider a given beam. So let's assume that you have a beam like this, and so we are going to assume that the longitudinal axis, the axis that defines the length of the beam, we are going to write it x. So x is going to be the longitudinal axis, and then usually we define as y the axis that is going up. So that if you look at this beam from the side, so you have axis x, which is the longitudinal axis of the beam that defines its length, and then you have the axis y that defines the height of the beam. So then if you have this beam like this with those two axes, then it means that necessarily you must have an axis z that is pointing in this direction, so that you form the x, y, and z axis form an orthogonal coordinate system. So then, based on this, after this, what we're going to do is to look at the property of the cross-section. So we take the cross-section, so we take a section of the beam that is orthogonal to its longitudinal axis. So in this case, that would look like this. And what will matter is what is the shape of this cross-section. So let's assume that we have a very general shape. So this cross-section, we are going to write it A. And so let's assume that we have a given cross-section like this with an arbitrary shape. So that's the area of the cross-section. So the first thing that you can define is the area of the cross-section. So when you have a surface like this, the first geometrical property that matters is what is the area of this surface A. So if you want to calculate this area, what you will do is that you will take every point M of this surface. For every point M, you will define an infinitesimal surface dA, where in this case, dA will be equal to a small variation of the y-axis times a small variation of the z-axis. And then you will do the sum of all those infinitesimal surface dA for all the point M belonging to the surface, and that will give you the total area of this surface. So in this case, to get the total area, what you need to do is to take the integral over the surface of all the small cross-section dA, all the infinitesimal cross-section dA. The second thing that matters, which is also an important geometrical property of a given surface, is its centroid. So the centroid is going to be located roughly at the average position within this surface. And so the centroid is defined as the point that if you take the surface and if you put the surface, for example, on your finger, the only point at which you can put this surface on your finger, and this surface is going to be at equilibrium on your finger and will, without tilting towards the left or towards the right, is going to be if you put your finger exactly at the centroid C of the surface. So where C, the centroid, is the geometrical center of this surface. So if you want to calculate the centroid of an arbitrary surface like this, you need to calculate what is the average position x and the average position y of this surface. The average value of x over the entire surface and the average value of y over the entire surface will give you the geometrical center of this surface, which gives you the coordinate of the centroid C. So in this case, if you want to find the centroid, so all you have to do is to find the coordinates. So typically, in this case, since the surface is defined along the y and z axis, the surface is in this case orthogonal to the x-axis. The x-axis is pointing towards you. It's orthogonal to this cross-section. Then if you want to know the position of the centroid, you need two coordinates. You need to know what is the coordinate of the centroid along the y-axis and along the z-axis. And since the centroid will correspond to the average value of y and the average value of z over this surface, then typically we can write the coordinate of the centroid as those y bar and z bar, which corresponds to the average value of y and the average value of z. And so if you want to calculate those coordinates, you would do exactly in the same way that you would calculate the average value of a given distribution. For example, if you want to calculate the average position y, then what you do is to sum all the value of y over the surface. So you take the sum, the continuous sum, so you take the integral of y over the surface, and then you divide by the total surface. That gives you, in the same way that you would calculate the average of the grades for a given class by summing all the grades and then divided by the number of grades. Here, if you want to calculate the average position y over a given surface, you are going to sum all the value of y and then divide it by the total surface. Same thing to get the average value of z. We are going to sum all the value of z over the surface A and then divide this by the total area of this surface, and that gives you the coordinate along the z-axis of the centroid. So this will give you now the position of the centroid C. And typically, once you have the position of the centroid C, what we will want to do is to define now C as being the origin of the coordinate system. So which means that if you define now the z-axis and the y-axis, which are the two axes along which this cross-section is contained, we are going to choose C as being the origin of those two axes. So where this would be axis Z and this would be axis Y, and C, the point C, the centroid, defines the origin, so that the value of the axis, the value of Y and the value of C is defined by convention to be 0 at the centroid. So we can always define the axis the way we want, but typically we choose the centroid of the surface to be the origin, so that the centroid now is going to be located at y equals 0 and z equals 0. And again, this is just because we define the axis like this. We define the axis to have their origin going through the centroid of the cross section. So now that we have the area and the centroid, now we can calculate the moment of inertia of this cross section. So, so for this, when you calculate the moment of inertia, there are two possible moment of inertia that you can calculate for a given surface. You can calculate the moment of inertia about the y-axis, or you can calculate the moment of inertia about the z-axis. And those two moments of inertia can be potentially important, and it depends for which type of bending you have. For example, if you have a bending like this, where this is the beam like this beam is subjected to bending. So in this case, you have the axis x like this, and you have axis y like this, and in this case, the axis z is coming towards you. Then in this case, it means that the bending is done along the z-axis. You have the rotation of the beam. The beam is now, used to be a straight line and now becomes a curve. And in this case, the beam is becoming a curve because, for example, it is subjected to some moments along the axis z. So z gives you the direction along which the beam becomes bent. So in this case, what will matter in this case is going to be the moment of inertia about z. But on the other hand, if now you think of a case where the beam is not bent about the z-axis, but bent about the y-axis. So for example, one way you can think about this is that if you have a beam that is initially like this, where this is the x-axis, then you have the z-axis like this, and you have the y-axis that is going up like this. Now, instead of, if the beam is not bent along the z-axis, but if the beam, for example, if you have a moment that is applied like this, so that the beam is bent like this, and now, so the beam becomes also used to be a straight line and now becomes a curve. But in this case, the direction of the bending is not about the z-axis. In this case, it's about the y-axis. The moment that are applied about the y-axis. So in this case, the geometrical property of the cross section that will control the resistance of the beam to some moment that are applied about the y-axis will be the moment of inertia about y. So in many cases in this class, we are going to focus on bendings that are applied along the z-axis. So we will focus mostly on the moment of inertia about the z-axis. But in general, again, there can be those two moments of inertia can be important. The moment of inertia about z and the moment of inertia about y. And the one that matters depend on the direction of the bending. So again, in this class, unless mentioned otherwise, we will focus on this case where the bending is applied about the z-axis. And in this case, what will matter is the moment of inertia about z. So now when it comes to the definition of this moment of inertia, so we're going to define those two moments of inertia, Iz and Iy, the moment of inertia about z and the moment of inertia about y. So if you focus first on the moment of inertia about z, the way we are going to define it is again by calculating an integral. So this time what we are going to do is to calculate something that is that looks similar to the average value of y square. If you calculate the position of the centroid, you want to find the geometrical center. So what you need to calculate is the average value of y. So that's going to give you the average position. Now, what we are going to do is to calculate the average value of y square. That's something that looks like the variance in mathematics. So what we are going to do is to calculate the integral over the cross-section of y square dA over the cross-section. And we integrate the value of y square, and that's going to give you the polar moment of inertia about z. Now, if you want the polar moment of inertia about y, the same thing. We are going to now integrate not y this time, but z. So we integrate z square over the cross-section. So if you look at those definitions, so when you calculate the moment of inertia about z, you need to integrate y square. And when you calculate the moment of inertia about y, then you need to integrate z square over the entire surface. So this is, in this case, the moment of inertia about z and moment of inertia about y. So what this moment of inertia means is that, again, you integrate the value of y square. So it's like y square, if you look at the surface for a given point m, y is its distance from the z-axis. So when you calculate the moment of inertia about z, what matters is, on average, how far are the points m belonging to this surface from the axis z. So for example, if you take a beam that is like this, where the beam is elongated like this, and in this case you have the z-axis that is like this, then on average, in this case, most of the points belonging to this cross-section have a pretty low distance from the z-axis. So that would be an example of a beam with a low moment of inertia about z. On the other hand, if you have the same beam now, but that is like this, so again, this is the z-axis. Now, if you look at all the point m that are located within this beam, they are on average pretty far away from the z-axis. So when you integrate y square over the entire surface, that is going to give you a high moment of inertia about z. Some other example of beams that have a high moment of inertia would be, for example, an I-beam like this. If you have an I-beam like this, and this is the z-axis, again, if you look at all the point m that belongs to this area of the cross section, most of the point m are actually very far away from the axis z. So an I-beam like this, due to its geometry, due to the design, due to the shape of this I-beam, a lot of the points are located very far away from the axis z. So an I-beam is a good example of a beam that has a high moment of inertia, and that's why I-beam are very commonly used in a structural application, because I-beam have for the amount of material that is used, they have a very high amount of inertia, because most of the material is distributed far away from the center of the beam. And because this beam has a high moment of inertia, it will tend to have a low stress. And because it has a low stress, then that is going to minimize the risk of fracture. So it's usually a good idea to have a beam like this that has the shape of an eye, because it tends to reduce the stress that the beam is subjected to, because it maximizes the moment of inertia. So when it comes to calculating the moment of inertia about a given surface, for a given surface, you will rarely have to solve the value of this integral. So to calculate for example, the integral of y square over the surface. And so there is one special case that can be very used, that can be commonly used, which is if the area, if the cross section is a rectangle. So in this case, if you have if the cross section of the beam is a rectangle, then we can derive a simplified formula for the moment of inertia, so that you don't have to solve this integral over and over. So in this case, so if you have a rectangle like this, so the axis Z would be like this, and the axis Y is going up. And so we are going to assume that this cross section is a rectangle that has a height H and a base B. And so the axes are defined so that the centroid is the origin of this axis. So then the question is, what is the moment of inertia about Z of this surface? So if we want to do this, so we need to take all the point M that belongs to this beam, define the infinitesimal surface dA, which is equal to dy times dz in Cartesian coordinates, and then we need to integrate to solve this integral over all the points M that belong to this surface. So what we have to do is to take the integral over all the position of this surface. So in this case, the point M of this surface will go for all the point all the points Z that go from minus b over 2 to plus b over 2. So that are the two limits of along the z-axis. And when it comes to the y-axis, it will go from minus h over 2 to plus h over 2. So we need to integrate the y square over all those possible values. So let's do that. So we will do the integral from ranging from z equal minus b over 2 to plus b over 2. Then we will integrate for all the value of y ranging from minus h over 2 to plus h over 2. And then what we are going to integrate is y square dA, where dA is dy dz. So one thing that we can do is to say that the terms, we can put together the terms that depend on y and the terms that depend on z. So in this case, this integral is going to be equal to first the integral between minus b over 2 to b over 2 of dz times the integral between minus h over 2 to h over 2 of y square dy. Then this integral here, if you integrate dz between b over 2, minus b over 2 to b over 2, what you get is simply b. And this integral here, so this integral is equal to the integral so it's equal to the integral of this is y cubed divided by 3, and you take this between minus h over 2 to h over 2. So if you do this, what you find is that this is going to be equal to so 1/3 of h to the power 3 to the cube divided by 8 plus h over 3 divided by 8. So this is equal to h to the power 3 divided by 12. So overall, if you combine everything, the moment of inertia about z of a rectangle is going to be equal to the product of its base b times its height to the power 3 to the cube divided by 12. So this formula gives you the moment of inertia about z of a rectangle. So if we look at the units of this expression, so the base, it's a length, so that's in meter. Then you have the height to the power 3. The height is also a length, so that's meter to the power 3. So this tells you that the polar moment of inertia is in meter to the power 4. So the polar moment of inertia, just like the moment of inertia about z, just like the polar moment of inertia, has a unit which is meter to the power 4. So when the beam doesn't have a simple rectangular shape, most of the time you still do not have to solve the value of the integral explicitly. Why? Because you can use this parallel axis theorem, and the idea of this parallel axis theorem is that if you have a beam that have a complex cross section, a complex shape for the cross section, then you can decompose this surface into a collection of smaller surface, a collection of a series of several subsurface, where each of those subsurface is a rectangle. And then that's going to give you a formula that can combine the polar moment of the moment of inertia of each of the subsurface, the rectangular subsurface, into the total moment of inertia of the entire cross section. So for this, you can use the parallel axis theorem. And so this is typically going to be useful if you have a beam that has a complex shape that can be decomposed into some rectangular shape. So for example, if you have an I-beam like this, so if you have an I-beam like this, and if you want to calculate the polar moment of the moment of inertia of this I-beam about Z, what you can say is that this beam is going to be a collection of this cross section. It can be a collection, can be decomposed into a series of rectangles. So there's different ways to do that, but you can say that, for example, this is this cross this part of the cross section, which is going to be this, plus this rectangle here, which is going to be this one, plus this rectangle here, which is going to be this one. So you can decompose the total I-beam into 3 rectangles like this that are located about the same z-axis. So the idea is that if you do this, you decompose this complex shape of the I-beam, the cross-section of the I-beam, into a series of 3 subsurface that are all rectangular and for which we can apply the expression that we previously saw. So we're going to see the expression, but there's different ways that you can decompose a given surface. For example, if you take the same I-beam again, another way to decompose this I-beam, which actually probably would be even better, is that if you have this I-beam like this and you would calculate the moment of inertia about Z, you could say that this I-beam is equal to a big surface like this, a big rectangle like this, from which you would remove those two rectangles. So you can say that this I-beam can also be decomposed as this giant rectangle minus those 2 smaller rectangles on the left and on the right. So that's another way to decompose this beam, is to say that you take this entire cross section here and you remove those 2 rectangles here. So that's another way to decompose an I-beam. So now the question is, if we know how to calculate the moment of inertia of those different rectangles here on the right, how do we convert them into calculating the moment of inertia of the complex I-beam on the left? So how do we go from what we know how to calculate, which are the moment of inertia of the beams on the right here, like the rectangle, because we have a formula from the rectangle, and how do we combine them to calculate the moment of inertia of the I-beam that is a more complex shape? So for this, what we can use is the parallel axis theorem. It gives you a way to calculate the total moment of inertia about Z in terms of the moment of inertia of those small rectangles. And for this, the formula is that you are the moment of inertia about Z of the total surface is going to be the sum, is going to be a sum over all the subsurface I, where I is equal to 1, 2, 3, etc. So those are this is the sum over all the subsurface through which the total cross section is decomposed. And then, so this sum is going to be first the sum of the individual moment of inertia of each of the cross of those rectangles. So for example, in this case, if you calculate the moment of inertia of this rectangle here, of this rectangle here, and of this rectangle here, so you will get 3 moment of inertia IZ1, IZ2, IZ3, or you can say this is IZ1, IZ2, and IZ3. And so the first thing that matters is what are the moment of inertia of those 3 rectangles, but this we can calculate easily because those are rectangles, so we have a formula for their moment of inertia. But then the second thing that matters is where are those rectangles located. And so the second term that will also matters is if you look at the centroid of those rectangles. So if you look at, for example, the centroid O1 of rectangle 1, or the centroid O2 of rectangle 2, and the centroid O3 of rectangle 3, in this case O1, O2, and O3 would be like this. The second thing that matters is where is located the centroid of those 3 rectangle with respect to the z-axis. And so this is going to define a quantity which is d1, which is, in this case, d1 is going to be the distance between the centroid to the axis z. So in this case, for example, that would be d3, which is the distance between the centroid of the subsurface number 3 from the z-axis. So then the formula that gives you the parallel axis theorem is that the total moment of inertia of the complex shape is equal to the sum over all the subsurface I of first their moment of inertia, the intrinsic moment of inertia of each of the surface I, plus the distance between the centroid of the surface from the z-axis, so the di, to the square, times the area of the surface I. So in this case, this would be the area of surface 1, the area of surface 2, the area of surface 3. So you calculate this quantity, so the product of the area of those surface times the square of the distance of the centroid of those rectangles with respect to the z-axis. So to summarize, in this case, the IZI, so IZI will be for each of the rectangle that you are decomposing, that you get when you decompose the complex surface. So for each of the rectangle I, you would have to calculate their moment of inertia. So this is the intrinsic moment of inertia of each of the surface AI. So that's the first quantity that matters. Then the second thing will be the AI is going to be the area of each of those subsurface AI. So if you decompose the total cross section into a series of smaller rectangle, each of those small rectangles will have a given area AI. And then the last thing that matters is DI, which is the orthogonal distance. The orthogonal distance between what? Between first the OI, where OI is the centroid of AI, the centroid of those surface AI, and the z-axis. The z-axis, the distance between the z-axis about which you're calculating the moment of inertia, and OI, the centroid of those surfaces. So for example, in this case, why is it better to decompose the I-beam with the second method rather than the first method is that if you decompose the I-beam using the second method, then in this case, all the centroid are all located along the z-axis. So in this case, all those terms here would be 0, because in this case d1 equals 0, d2 equals 0, and d3 equals 0, because the centroid of those three rectangles is located on the z-axis. So all those terms would be 0. So all you would have to do is to calculate the moment of inertia of each of those three rectangles. So now, when you do this decomposition, the other thing that matters is the sign when you sum those moment of inertia and those area and distance from the axis z. When you do this sum, you sum positively if it's a surface that you add. So, for example, in this case, when you use the first method, you say that the total surface is the combination of this surface plus this surface plus this surface. So in this case, you add those three surfaces, so you would add a plus sign. But on the other hand, if you use the method 2, then you would say that the total surface of the cross section would be this. So you add this surface, so that would be a plus sign. But in this case, then you remove this surface, and then you remove this surface. So when you do the sum, when you remove a surface, then that should be a minus sign. So for example, in the case of the second method, then the way you would calculate the moment of inertia of the total cross surface would be to say that in this case, this is going to be equal to the moment of inertia of the surface number 1, because you add this surface, minus the moment of inertia of surface number 2, because you are removing this surface here, minus the moment of inertia of surface number 3, because you are removing this surface. So you should have in this formula a plus sign if you add this surface, or a minus sign if you remove this surface. So now that you have this formula, what you can do is that for almost every cross-section, for every shape of the cross-section of a beam, you can most of the time decompose this beam into a series of rectangle by simply adding or subtracting some rectangle, and then use the parallel axis theorem, because you know how to calculate the moment of inertia of a rectangle, and then you can combine all those moment of inertia to then calculate the total moment of inertia of the complex beam, like for example in this case for this I-beam, or for any other shape of the cross-section of the beam. And once you have the moment of inertia, this is going to give you the geometrical quantity, the moment of inertia about z, that dictate the resistance of the beam to bending about the z-axis. So this moment of inertia is going to be a key property that will be useful when we calculate the stress that is generated within a beam that is subjected to bending.